let's move to the next talk, which is by Kirk Barrow. And Kirk will tell us about unraveling time-dependent trends in star formation using cosmological simulations.
Great. So, hi, I'm Kirk. I'm a postdoc at Stanford University. And this title seems like what everybody's doing, but I'm coming at it from a little bit of a different angle. And to sort of introduce my work a little bit, I wanted to put up this really simple map. So you can think of the beginning of the universe as the left side and the present day as the right side. And, as Eli said, cosmological simulations, hydrodynamic simulations are computationally expensive. And in order to sort of move to the present day with them, you have to either make sacrifices in terms of their size or complexity, or you just can't do it. And then, of course, on the telescope side, we have a fairly clear picture of what's right next to us. And as you go deeper into deeper fields, it becomes a lot hazier. And of course, we don't have a direct sort of infrared or optical view of reionization, and we're waiting for that with telescopes like JWST. So my research is focused primarily on a region of overlap, and that region of overlap is, it's not focused on a particular redshift. It depends on the way that you're overlapping observations and cosmological simulations. But no matter what you think of as the overlap region, you have to speak a common language between the two sort of different fields in order to iteratively improve our understanding of the universe. So the common language, I think, is through light, and that means that I need to make cosmological simulations, something that looks like what the observers see, which is luminosities, images, spectra, and things like nebular emission lines. So nebular emission lines are important for a lot of reasons. As we know, nebular emission lines are really sensitive to really small changes in the hydrodynamic environment where they're created, and they therefore, because there's so many of them, they sort of serve as a fingerprint for the environment of the galaxy, and you can sort of understand a lot about what happened to that galaxy from the nebular emission lines. On the modeling side, it's actually somewhat of a difficult problem to reproduce nebular emission lines, because they're sort of produced all throughout, a inhomogeneous H2 region. So if we sort of look at this toy model of an AMR simulation, nebular emission lines are not just coming from the cells that contain star particles, they're actually coming from all the cells in some form or fashion. And the H2 regions that are produced from these star particles are not spherical, they're not, the gas is not homogeneous, and you have to think about all the different combinations that you could have and the full radiative environment in order to reproduce a nebular emission line. But it's worth it, because if you can reproduce nebular emission lines, then you can talk directly to observers about the detailed microphysics, the kind of things that we're talking about during this conference, the star formation physics that occur inside of galaxies. So hopefully I've convinced you that nebular emission lines are important, because I haven't heard them talked about too much so far. But I think a lot of people agree that time domain studies are important. Almost everybody so far has done something in the time domain and talked about the redshift dependence. But working on synthetic observations, I didn't start in the time domain. I actually started with the Renaissance simulations that Eli brought up, and it took one single snapshot and looked at all the galaxies within that snapshot, made synthetic images and spectra and nebular emission lines. And it was a good statistical sample, but from a single snapshot, of course, you can't figure out where, directly you can't figure out where all of these relationships came from, and you really need to think about a dynamic, the full dynamic environment to really understand where all of these observables are actually coming from. So while we wait for that region of overlap between observation simulations to move into reionization with JWST and maybe a moon colony with a big telescope, one of the things I've been doing is I've been looking at how do we move a little bit closer to the present day and make comparisons with observations we've already seen. But I want to motivate time domain studies, especially when it comes to not only galaxy formation, but with observations. So why do we need time domain studies at all? And why don't we just use a semi-analytic model to make up for that with, instead of using those really computationally expensive cosmological hydrodynamic simulations? And the reason is because early universe galaxies, or one of the reasons, is early universe galaxies have birthday star formation histories. They're irregular. You can't really always assume spherical symmetry. They have high merger rates, and mergers are really messy processes. So this sort of challenges a lot of the semi-analytic notions, and when it comes to reionization, this is where we really need to get these things right. These images I'm showing in the background of these movies are Monte Carlo ray tracing optical images of galaxies. So here's two galaxies merging, and these events that happen, these really large star formation events that happen, these small halos, they're really disruptive. And if you don't get the feedback right, if you're not modeling all of the feedback, you might actually miss the boundary between a galaxy that continues to form stars and goes about its business, or a relic galaxy that's completely disrupted. Like, you need to really understand the difference, because if you're trying to make predictions for observations, those are two opposite scenarios. You really need to understand that difference. And then the last, pitch I'll make for doing time domain studies with synthetic observations is that if you look at a single snapshot like I did, in order to produce that snapshot, of course, you've calculated all the intermediate time. And it sort of turns out that the parameter space of synthetic observations for a single galaxy is quite large over its history. And so to only look at one time step is to throw out all of that information you've already calculated. That is actually quite as interesting as any individual time step. Okay, so let's talk a little bit about the first stars and this critical mass question that keeps coming up. Now, before Mihir's talk, I would have said, okay, I have a wonderful simulation with really high resolution, and that minimum mass shown in the top left as this vertical line seems to be consistent with Anna. I'll have to look at that again in case things are changing a little bit. But one of the interesting things, I think, to some of the other presenters and in the audience is actually this internal enrichment, external enrichment question. And what I'm seeing is that, as people talked about, that a dynamic, fully resolved, hydrodynamically calculated external enrichment is actually causing it's actually suppressing population 3-star formation after some point. It's changing the critical mass, and these processes really need to be untangled before you make sort of broad sweeping statements sometimes about the critical mass. And this is something I'm really interested in looking into in the future. But that's not the whole of my wheelhouse. My whole of my wheelhouse is mostly in synthetic observations. So these hundreds of galaxies that I'm simulating are going to be turned into synthetic observations. And you kind of caught me while I was working on that, but I want to show an example of where that comes in. So this is an example of synthetic observations that you can make from a single galaxy. So you have the spectra, you have the emission lines, you have escape fractions, you have the galaxy. But how do we actually use this to answer questions with observations? So here's a bunch of observations. This is the emission line ratio between O3 and O2 versus the escape fraction ionizing radiation. And the question was, why do we see top left of that chart, why is it empty? Now there's some lines you see in there. That was based on sort of preliminary observations, and that's sort of been debunked a little bit by the present observations, but there's still this missing part on the left side. And how I sort of looked at this is that first, I had my toy model to see what happens with a single cluster, and it turns out that emission lines are actually quite sensitive to different phases in this evolution of stars. And then I have my full model, which solves the full radiative environment and creates emission lines throughout the galaxy in sort of a generalized way. And you can actually see as the yellow line, the ratio between the lines. And I found that the escape fraction of ionizing radiation and O32 were offset because of the different timescales of the processes, where O32 was really, O23 was really responsive to recent star formation, and the escape fraction had a longer delay time. And it sort of turns out that because I'm looking at all of the time, all of the history of this galaxy, so there's actually thousands of outputs that have analyzed and created synthetic observations for. And then the orientation of the galaxy is important for escape fraction, particularly because escape fractions are highly anisotropic process that really depends on the morphology of the galaxy and where the neutral gas is. It turns out that you can create millions of possible synthetic observations from a single galaxy and start to reproduce the observational landscape shown here. So so this is sort of my most recent work, but what I'm really looking forward to is turning that reionization simulation into hundreds of copies of that and creating a predictive landscape for our next generation of GMT and our large telescopes as well as JWST. So that's what you can look forward to from me. And to summarize really quickly, you should care about nebular emission lines because they're going to help us solve some of these questions. Time-dependent studies are good. And it turns out that O32 is not linked to escape fractions in a causal way. It actually has to do with a timing issue. So I'll wrap up there. Thank you, and I'll take some questions.
Thanks, Kirk. This is great additional information on the early star formation. So I actually I don't yet see any questions on Slack, but I did have several. Let me just ask one because we're also slightly late. Is just observationally, can you give an idea of are these lines all going to, how many or which lines are going to be measured at high signal to noise by JWST and GMT, and do we have do they even resolve the kinematics or width of these lines so that we can study them in some detail?
I mean, that question depends on redshift. I'm actually
let's say redshift 10. I mean, can you go into the halos at the critical mass and see their nebular lines? And to
I don't expect you to be able to go to the critical mass, but I will say that when I speak about emission lines, you know, after sort of basing my initial postdoc proposals on JWST, I've taken to overlapping with current observations, so things at redshift 3, 4, 5, and 6. And so if you're waiting for the most forthcoming things that you're going to see from me are going to be focused in that area. So we'll see what GMT provides, and I'm really looking forward to JWST as well. But I don't, though, predict that the critical. So maybe in the future, maybe on side, we can talk about that. I think there's a way that you can constrain that from what happens at redshift 5 and 6, but I think that's a different question.
Okay, so maybe, so now you do have a lot of questions that popped up, including people want your movies shared. So do go to Slack. Let me just ask one of the questions, which is, if you smooth this from Yu Chiang Chin, if you smooth the escape fraction over a longer period of time and introduce time delay, would it align better with the O32 indicator?
No. So the initial, and I didn't have really time to go into the depth of that. So the initial thought, I guess not really initial, from like early 2020, was that the reason that they're related in any way is maybe because you're seeing the O32 through the same ionized channels that you're seeing escape fraction. And it sort of turns out that that can't be because O32 is an optically thin line. It isn't absorbed by the medium, so it shouldn't really be related to escape fraction. If escape fraction is something that is related to the orientation of your line of sight. So, but to answer your question about smoothing it over, no, there's sort of a systematic delay between the formation of a star cluster and the ionizing radiation actually getting outside of the galaxy. So, and there's almost no delay. There's only a few million years delay for the 032. So there's just sort of a systematic difference between the two. And I invite you to read my paper to read a little bit more about that.
Thank you. Thanks, Kirk, again, for a very nice talk.